So for our first talk, we have here Joe Blass, who is going to be talking on conclusion-verified analogical schema induction.
Hi, everybody. Thanks for being here. I'm Joe. I'm a member of the Qualitative Reasoning Group at Northwestern. Like Willie said, I'm going to be talking about conclusion-verified analogical schema induction, or CASI. Acronyms are hard. I'm happy to form a support group if anyone's interested. So CASI is a concept learning algorithm, and when you're learning concepts from examples, there's many different approaches that you might take, and these are going to depend on factors like the nature of the data, how are they represented, are they labeled, how are they labeled, how much is there, and the nature and the use of the target concept. What's the use case? What's the form that you're trying to learn? CASI is a concept learning algorithm that works on data sets of labeled predicate logic cases. They can be small data sets, and it builds probabilistic schemas of those cases. So here's the outline of the talk. I'm going to talk to you about the background tools that we came in with, the problem that we discovered when working with a certain kind of data set. I'm going to tell you about the data set in particular that presented that problem and the solution we came up with, and some experiments that we used to evaluate that solution. I'll finish with discussion and future work. So let's start with the structure mapping engine and SAGE. So SME, structure mapping engine, is a computational model of analogy based on structure mapping theory. And it constructs mappings between two structured relational cases. So if you have these two cases where in one, Ari threatens Blay, which caused Blay to be afraid, Blay's fear caused them to hide, Elith saw all this, and Blay's fear caused Elith to help Blay. And now we're in a new case where Charlie is threatening Drew, which causes Drew to be afraid, and which causes Drew to run away, and Elith wants to know, what do I do in this situation? SME will construct a mapping which establishes correspondences between these cases, uses those correspondences to project candidate inferences. And it also will include a similarity score that evaluates the quality of the match. And this similarity score is driven by shared structures, not isolated correspondences. And so the deeper the structures that are being mapped, the higher the score will be, not just as a function of what's being put in correspondence. Okay. The sequential analogical generalization engine is a tool for building analogical schemas. For each concept, it has a generalization pool case library that will include generalizations that have already been formed, that have been merged from two or more examples with probabilities for each statement in the example. And it'll also include outliers that haven't been assimilated yet. And it takes in a sequence of cases, and each case is used as a probe to retrieve from that case library, from the G pool. And then the retrieved case is compared with the probe case using the structure mapping engine. And if the similarity score of that match is above some assimilation threshold, then the cases will be merged together. So if the retrieved case was a generalization, then the new case will be merged into the generalization and the facts will be updated. If it was an outlier, then they'll be merged into a new generalization. And if the SME score was below the threshold, then that probe case will be added as a new outlier that can potentially generalize with future cases. The problem comes when you're using cases that have particularly flat representations that don't have those deep shared structures that can be mapped, and that might contain distractor facts that will essentially lead SME to map the wrong things together because they look the same. So I'll give you an example. So sometimes cases have these flat representations, meaning they don't take other statements as arguments, and this leads them to have very low match scores. And in particular, cases that are good matches with each other and cases that are bad matches with each other might have very low match scores just because there's no deep structure to show that it's a good match versus a bad match. And in that case, SME's match score alone can't discern useful from useless matches, which means that match score is not, it can't be used as an assimilation threshold sweet spot for SAGE generalization. If the threshold is set too high, then nothing will generalize together. If it's set too low, then bad mappings that we know are bad, will generalize just as well as mappings that we know are good because the similarity score isn't distinguishing between them. So this is an abstract description, so I'll get more specific. We're doing this on this data set, the Illinois Intentional Tort Qualitative Data Set that I developed as part of my thesis work. This data set contains cases, tort cases, and assault, battery, trespass, and self-defense, both positive and negative cases, meaning did the person actually trespass? If yes, that is a positive case. If no, it's a negative case. The data set includes, for each case, there are semi-automatically produced predicate logic representations produced from simplified English descriptions of the case facts. And the idea behind my thesis, when I set out to do this, was to learn what facts underlie each tort claim by feeding those cases into Sage and letting Sage figure out what facts the cases have in common. So here are two examples of the cases. I don't expect you to read all this. This is very long. In the first case on the left, Trout, a plaintiff, dies when he drives his motorcycle into a bank's parking lot at night, and the exit of the parking lot is blocked by a chain. And so the trespass claim here came as a defense to a wrongful death lawsuit, and the bank was saying, we're not responsible because the person was trespassing, and the person was trespassing. And in the second case, the defendant cut down a fence that straddled his and the plaintiff's property. And then there are some separate facts in the case about things that were going on with the plaintiff's father, who was the prior owner of the property, including that he died. And this was a trespass because the fence was on the plaintiff's property when the defendant cut it down. And these aren't all of the facts of the case because I couldn't fit them all into a slide. This is just the predicate logic representations aren't all of the facts. This is just to give you an idea. And in particular, you might be able to tell that these have flat representations in that the statements are all predicates with single entities as arguments, as opposed to statements where it's a predicate where the arguments are other statements, okay? And the point here is that these two cases should not be combined together. The second case, Conklin, about cutting down the fence is an outlier. It's unusual in our data set. And the first case, Trout, should generalize with an as yet unseen case, Falachik, which concerns a defendant that turned part of his neighbor's property into a parking lot and was parking his car there. And the mapping between Trout and Falachik looks like this. So you have a mapping of someone owns some sort of property, right? In Trout, it's the defendant who owns a parking lot, and Falachik, the plaintiff, owns their own property. You have the fact that someone else drives onto that property and then is found in that property, and it properly aligns the trespass conclusion facts. These two facts at the bottom aren't perfect alignments and aren't necessary to align in the case properly, but it captures what should be aligned about these cases. On the other hand, the two cases that I showed you, Trout and Conklin, can't map well. So this mapping is what we get when we require the trespass conclusion statement to correspond, which we have to do if we're trying to learn about trespass, then those two things need to correspond. By default, it won't even align them. And it puts into alignment the fact that there's a death in both cases, but that's not actually relevant to the map at all. This just isn't a helpful map, and it doesn't help SME learn anything about trespass. The problem is that the scores here are essentially the same, and they're very, very low. So the score for the bad mapping is 0.04. The score for the good mapping is 0.07. These are very low scores. You might think, well, can you just set the assimilation sweet spot to 0.05? We tried that. It doesn't work because of other cases that have other thresholds. And so either the assimilation threshold is too high for Trout to generalize with either case, including Falachik, or it's low enough that if Conklin is already there when Trout comes in, or if Conklin comes in before Falachik, then the retrieval system will preferentially retrieve Conklin, the bad case, when it's presented with Trout, and it will generalize them together because its score is above the threshold if the threshold's low enough. So the key point here is that, these cases can map in a way that captures useful information, but if Sage is going to use those mappings to determine when to generalize cases together, Sage needs criteria besides the match score to guide generalization. And so that's why we developed conclusion-verified analogical schema induction. This was a necessity is the mother of invention situation. So here's the idea. Casey provides an alternative consistency check to validate a mapping for generalization. So given a probe, this case here, and you can see that this is the Trout case. The plaintiff is driving into the parking lot that the bank owns. You can see that these are these flat representations, right? There isn't this deep level of structure. So given that probe case and the form of the relevant conclusion C, which is the trespass fact on the right there, and some generalization pool, the Casey algorithm starts by removing the conclusion from the probe and then retrieving from the case library using the truncated probe. It creates a mapping from the retrieved case to the probe. So in this case, the retrieved case is phalangic, the good map. Of course, in our experiments, it would retrieve the bad case first, but this is to illustrate how it works under the proper circumstances. So it makes that mapping, and it inspects the mapping to see whether the conclusion statement that had been removed is now projected as a candidate inference. And if it is, it puts the fact back into the probe, and it uses the mapping to generalize these two cases together. And this is sort of like asking, could this mapping have solved the probe case if the solution to the probe case was unknown? And if the answer to that question is yes, then we think that it is capturing a mapping of useful facts between the cases that capture some sort of connection between the case facts and the case conclusion, or at least it's capturing case facts that are reasonably associated with the case conclusion. And this is as good a place as any to note that we're not presenting this as a model of human cognition. We have ideas about that, but we don't have evidence. I'm happy to talk about that if people have questions about it. A couple notes about KC at runtime. So you do have to be able to identify the case conclusion. This is supervised learning. It's not quite a label because it's a fact in the case that you're trying to learn about, but that is sort of a label. You have to be able to recognize the predicate that you're looking for. So you don't have to know ahead of time what the specific conclusion in the case is going to be, but you have to be able to recognize it. It's also less efficient than Sage. Sage will use the first retrieval that it gets to reason with. KC will continue retrieving cases and scrutinizing mappings until one passes its test or it runs out of cases to retrieve. It would be trivial to add a depth limit. We just didn't do that for our experiments. But if the depth limit was more than one, it will be less efficient than Sage. And I also wanted to note that in our investigation, KC usually didn't sift through mappings from the same retrieved case, meaning when you're mapping two cases together, you might have multiple different ways to map it. And one thing that you might think KC could do, and maybe it would do this with other data sets, is it would throw away the first mapping between two cases and it would use the second one. But what KC was really used for in this situation was rejecting the cases that formed bad mappings in order to get to the one that would form the good mapping. And we found that SME was consistently forming the right mapping the first time once it got to the right case. So let me tell you about two experiments that we did. So in experiment one, we created generalizations from that legal data set using KC and using Sage, and we examined those generalizations to see which one captured more core doctrinal facts about the legal claim in question. And then in experiment two, we used those learned generalizations for the legal reasoning task. And we didn't test these on self-defense cases. Very briefly, self-defense presents a particularly difficult and different kind of tort legal reasoning than other cases, because you first have to establish that the claim was met and then have to reason in the second step about what's happening. And then I also wanted to mention that we only tested these on positive cases because it's positive legal cases that actually encode the facts that underlie the legal claim at issue, right? The only thing that negative trespass cases will have in common is that they didn't contain the facts that lead to a positive case. So when you're thinking about learning concepts in this domain, it's the positive examples that contain those concepts. Negative examples can be used as near misses to sharpen the category boundaries, but we didn't do that in these experiments. Okay. In the first experiment, before running the experiment, we defined which facts were necessary to infer that a legal doctrine was met, just to keep ourselves honest, so that we did this before looking at the generalizations. In trespass, it was either 4 or 5 facts, depending on what was on the property. So the person trespassed upon owns some property, the trespasser goes onto that property, or they own some object that goes onto the property. They're the one doing the event, and then the event brings them onto the property. For assault, it's more straightforward. A threat occurred, it was performed by the assaulter, it was against the victim. For battery, a touch occurred, it was offensive or harmful, performed by the batterer against the victim. And I wanted to note, before we get to the results here, that trespass cases are a little trickier than assault and battery cases, because assault and battery cases in our representation system that we get out of the language will use predicates that are specific to assault and battery. So for assault, if you have a threat entity, the predicate associated with the person making the threat and being threatened is threatening agent and threatened agent. Whereas with trespass, it's these predicates like object acted on and performed by and done by that are used in a lot of different contexts, including like ownership, like an ownership event is performed by one agent and acts on some sort of object. And so that's more confusing. So after we pre-generated these facts, we manually inspected Casey and Sage generalizations to see whether those doctrinal facts were present. And we coded those generalizations into 3 categories. So a correct generalization contains all the doctrinal facts. A partially correct generalization is missing 1 fact, so it's most of the way there. If there were 2 or more doctrinal facts missing, then that was a false generalization. Here are our results. I know it's a lot of data. We go through the results in more detail in the paper. So first of all, Casey made more generalizations than Sage, and it also used more of the cases when it was making those generalizations. It left fewer cases out. That doesn't mean necessarily that those cases are better. The generalizations are better, but Casey made more correct trespass generalizations than Sage. And in fact, Sage was essentially unable to make good, correct generalizations out of the trespass cases. It got 0 correct generalizations out of those trespass cases. Again, we think it's because it's using these predicates that show up in a lot of different contexts, and so it can't link them together properly. Casey also made more partial or correct generalizations across the board, and fewer false generalizations than did Sage. But the point, of course, isn't to admire these generalizations, it's to use them. So in experiment 2, we actually evaluated these generalizations and how they performed using the legal reasoning task. The point of the talk is not the legal reasoning task. That's presented in other work, although I'm happy to talk about it. It's just used for the evaluation here. We tested 2 algorithms of our own and a machine learning baseline. So our first algorithm, analogical reasoning with positive generalizations, or ARPG, applies those generalizations of positive cases by analogy to new cases and examines the candidate inferences to determine whether it's a positive, for the legal conclusion, and to determine whether it's a positive or negative case. It's possible to run ARPG with a partial truth test to determine whether it's getting close to the answer, so we ran it both ways. And we used precision at 6 here because at reasoning time, retrieval is challenging for the same reason that it's challenging when you're producing the generalizations in the first place, right? These cases are very flat and they share a lot of different predicates with each other, even when they aren't necessarily conceptually similar to each other. And so for the same reason that we needed to develop Casey in the first place, it was difficult to assess. The right case was rarely retrieved the first time around. And so we tested it with precision at 6. Our second algorithm we call reasoning with rules learned from generalizations, or RLG. Essentially, we just convert those learned schemas into horn clauses, and then we apply the horn clauses to held out cases. If the horn clause fires, then we say, this is a positive case. If it fails to fire, then we say this is a negative case. We did not prove the legal antecedents that would have turned this into a successful legal claim. And then our baseline was LegalBERT, an LLM BERT model specialized on legal documents. We turned the cases, we tested it on the simplified case descriptions, and we turned the case conclusions into a 4-way multiple choice test and just had it select amongst those choices. I'm happy to talk more about that. So here's our results. There was no significant difference when using Casey or Sage, either when using the analogical reasoning with positive generalizations, analogical reasoning system with a strict truth test, or when using the rule reasoning system. But Casey significantly improved the performance of the analogical reasoning system when it was using a partial truth test. So we think there's clear evidence here that it is capturing some useful domain information, and it's not necessarily all getting used properly, but it is being captured. I also wanted to note that all of the methods improved on the trespass cases. The trespass case improvement was what drove the results with the partial truth test to statistical significance. In the other methods, it was a trend, not statistically significant, but they all improved across the board on trespass. And I wanted to make a note about the rule reasoning system's lack of a difference here, which is, think about how this rule reasoning system is working. If it's firing the rules learned from a positive case, if they fire, the case is positive, if not, the case is negative, that means that learning bad rules will lead to improved performance on negative cases. right? Because the rules never fire successfully. And on a negative case, that counts as getting the case right. The rule didn't fire. And we see indeed that for Sage, the negative case performance is perfect, but the positive case performance is worse than with Casey. So even though the statistics aren't showing that Casey is helping relative to Sage, we actually think that this is providing evidence that Casey is capturing useful information that's just not being borne out based on how the evaluation is working. So I'd be interested to learn how to disentangle that a little bit. And then the analogical reasoning system, when using a partial truth test, beat legal BERT when using Casey, but not when using Sage. The rule reasoning system consistently beat legal BERT regardless of which algorithm it was using. Okay, so we think that we showed that Casey can capture useful conceptual domain information in situations where Sage is unable to, for the reasons that I said. And where Casey most improved the generalizations, that it led to improved performance when reasoning with those generalizations. A couple of reviewers noted the similarity to inductive logic programming in that both ILP and Casey learn concepts from examples by stripping away extraneous information. Just want to note a couple differences in that Casey doesn't generate rules, it generates schemas. And Casey maintains outliers within its model that don't fit the model being learned. We see two big areas of future work in improving and in expanding Casey. So clearly there are some relevant facts that are still being omitted from many generalizations. There are extraneous facts that are making their way in. We'd like to investigate why there isn't greater improvement on the rule learning system beyond the factor that I described earlier. And it would be useful to incorporate near misses and those negative cases to sharpen category boundaries. In terms of expanding Casey, we'd like to test it on other data sets and in other domains, and in particular to see whether it improves performance on data sets where Sage is already effective. And we might be able to use, we're thinking about being able to use a Casey-like check to improve the retrieval process and make retrieval more effective to not have to go through so many cases at retrieval time. And that's it. I'm happy to take questions. Thank you.
Great. Thank you, Joe. We do have a question here on Slack. So Chris on Slack asks, does Sage have the ability to undo generalizations and redo different generalizations as new examples come in?
Oh, that's an interesting idea. No, it does not. I don't know if we've investigated that. That's a good idea. Yeah.
I'm also going to invite people to come to the microphone so we can get to the questions going quickly. So I believe we have another question.
Yes, so great talk. If you have a problem where you've got the facts of the case and everything's too flat and you have no relations and stuff, strikes me that one thing your stuff might be useful for is to, I mean, you don't have it in your scenario where all the cases, the facts are listed in advance, but if you're an attorney trying to figure out what questions to ask about a case, then that might help you determine what are good questions to get, so the good questions are the ones that give you the structure you need to do the legal reasoning. So that might.
That's right. Yep. Yeah, I mean, legal cases are all about the structures that are connecting their facts to their conclusions, right? The reason that those aren't present in our data set is that it was important to us to generate our data set using a semantic parser from English rather than hand encoding them. And those structures can be very complicated to express causally. You're referring back to a bunch of different things that have been referred to. And so we made the decision to leave them out rather than, we were really faced with a situation where we could hand encode them versus leave them out entirely. And so we decided to leave them out. And like I said, it's because of that that we had to develop this algorithm in the first place because we weren't making headway without those deep structures. But yes, I think that you're right.
Thank you.
Similar question. Yeah, really interesting talk. And I found myself wondering during the talk whether there are certain things about the nature of what is appearing in these case facts that would shape the performance of these of the algorithms. You mentioned, for example, that in one of the cases, the fact that somebody died was in there, but it was a case about trespass. In this sense, this wasn't really relevant, but it was in there anyways. And on the other hand, surely there were innumerable other irrelevant facts that didn't show up, but they weren't in. weren't in there for different reasons. And so I'm curious if they're for the types of things that were irrelevant, whether there was something about the irrelevant things that were included that in some way shaped the performance.
Yeah, so if I'm understanding the question correctly, I think the point is that sometimes, all of the cases contain irrelevant facts.
Right.
And it just so happens that sometimes two cases that aren't a good match will share enough irrelevant facts that the retrieval system will propose it because it just looks at what kinds of facts are present in each case and it just grabs them. It grabs the case, right? And then once it has them, SME will put those into alignment because that's what it's working with, right? There are other cases where the fact that someone died is a relevant fact, right? It's not often relevant in trespass, but it is relevant in other cases. And so there's no way to kind of specify ahead of time what is going to be a relevant or irrelevant fact, right? And the point behind doing this is that the mapping of the facts alone doesn't tell you whether they're relevant or irrelevant unless you can somehow connect it to the conclusion, which they weren't without the structure. And so, it's sort of a way of getting around the issue of determining them. I feel like I didn't answer your question though.
No, I think the issue is my question was ill-posed, but
I don't think so.
Thank you.
Thanks, Joe. You had me thinking about why it was you weren't using the negative cases, and maybe this was not only for the reason why you explained, but also because there's just too much work involved to try to leverage them. But I was thinking that just like in the idea of generating synthetic data, you could imagine if a lot of work was involved, you could develop a way to generate counterfactual variants of those negative cases so that they could be used for purposes of training. Is that something feasible?
Yeah, and I would go a step further than that and say some of the cases in our data set, these were all real historical Illinois cases, and some of them came from cases that were on appeal, where the appeals court was saying, we don't know what the facts are. And so lower court, figure it out. If the facts are this, the person trespassed. If the facts are this, the person didn't trespass. And so they're highly alignable with each other, and they should be useful to do that. So that's one way to generate counterfactuals, is to even go to what the courts themselves are saying. The main reason we didn't do it in this work is just that we didn't get to it yet.
Right.
But I think that's right.
Second point is that if you ever decide to apply this to problems of baseball, you could call this KZ at the bat. Something.
We do have time for a couple more questions, and so I'm going to take a minute to ask a question myself. With Casey, if I understand right, you are removing some of the probe, seeing if you are still able to make a good analogy and be able to make the inference that you're trying to make, and if so, then yes, that is the type of generalization you want to create. And you do this because it's a very flat structure. And obviously I'm very sympathetic with this problem. And I was wondering about why not, instead of kind of taking something out, trying it, and then putting it back in, of actually then introducing some higher order structure. Being able to show that the set of facts over here relates to this fact over here by this is kind of the conclusion, and these are the facts leading to this conclusion. Did you try something like that?
No, I think that's a great idea. I think that when I had started doing this, I thought that that's what I was doing, and then I didn't get around to the last step of actually connecting those facts to the conclusion. I think that's a great idea, and I think it would be a relatively straightforward extension. I think the tricky part would come from the fact that these Casey generalizations, even though they're much better than the SAGE generalizations on this kind of data set, they do still include some extraneous facts that kind of have nothing to do, like, you don't have to be driving a car in order to be trespassing. It just so happened that we had a bunch of cases where they do, right? And so that driving a car fact made it in. And so before being willing to go out and I think conclusively tie the facts that are being identified directly to the conclusion, I would want to get a little better at stripping those facts out. Now, one way that might be possible is to see which parts of the cases are being used in solving future cases, and continuing to you don't necessarily need to know how the future case comes out to be able to see what's participating in a mapping from the learned generalization to that future case. So that might be one way to get at it. But I think that's right. I mean, the point is not just to see which of these facts hang together, it's to see what is causing the conclusion to show up. And yeah, that would be an eventual goal.
So there are a couple more questions on Slack. In particular, one question from Chris is your data set available online for other users?
It is about to be. Yes, thank you. I am going to be doing that within the next couple of weeks, and I will link to it from our website.
Great. And there's also a couple of questions on analogy and structure mapping. How efficient is the structure mapping process, and are there heuristics to constrain the space of possible mappings?
Yes, so if I'm not mistaken, the computational efficiency of the structure mapping engine is n log n, or it might be log n. Do you know? I think it's n log n.
I think it's higher.
You think it's higher? Okay. That I can get back to that. I know that that's in the structure mapping papers. And so if you look, there was a paper in 2017 on the structure mapping engine where it talks specifically about that. And it also talks about the kinds of constraints that are possible. So you can require two facts in a particular case to be, in two different cases, sorry, to be put into correspondence. You can require that just one of the facts be put into correspondence. So there are control, and there are others as well, but there are control systems that you can use in making the mapping. And then the structure mapping engine itself has built-in constraints. So one-to-one mapping, things in one case can map to at most one thing in another case. Parallel connectivity, if a statement maps, then its arguments must also map to each other, or at least must not be mapped in a cross-purpose way. So yes, there are, and I urge people, if they're interested, to check out the latest SME paper. SME is definitely publicly available for use in a variety of domains, and you don't have to use it. It works on predicate logic representations, but it is like ontology agnostic. You can use it for a variety of different purposes.
And Ken chimed in. It's n squared log n.
N squared log n. Thank you. Did you? Yeah.
What language is it written in?
It is in Lisp.
SME is available in Common Lisp.
Common Lisp.
Common. Yeah, just SME is available in Common. Any other questions? All right, let's go ahead and thank our speaker.
Thank you all so much.